Okay. Coffee? Caffè? Yeah. weet niet of mensen weten precies hoe het fluxgebouw is, ook voor het eerst dat ik het niet weet.
Ja,
Helemaal niet.
maar er zijn veel mensen die dat ook niet.
Ja, dat is...
Ja, ik heb het van
Oké, ja, dat is het.
ja. En de industrie.
Oké, ja, oké. Ja, leuk.
En de kamer.
Oké,
Schizzo le scene della Corea con sì, sono sì.
ja, is meer in NWO natuurlijk.
Ja.
Ja,
No, bueno, si crea se no, perché non ha le mie scale.
NWO ja. Maar dat is dan echt voor de stijl.
Ja. Nee, maar misschien moet je het zo doen, toch?
Ja, dan heb ik nog snel. Als ze nog steeds kunnen met hele vragen zijn. Hey, die ook nog uitgezocht wordt. Maar dan zit je toch meestal. Ja. Dat is wel een beetje die meer. Dat is wel fijn. Zeker, ja, zeker. Nog niet meer als we weer buiten.
Ja.
Maar goed, dat is wel onze spanning. En dat is een beetje van de steeds. Het zit wel heel leuk. Ja.
Ja, maar ik ben wat het is op de hele institutie. En dan ben ik meer dat iets die op de soort zijn.
Nee, oké. Ja, dat is ja.
Ja, dat is een hele keuze. Ja. Je hebt echt heel veel zien. Heel veel staan.
Ja, eigenlijk een weer in de bouw. Het is niet wat heel breed. Ik weet het al niet.
Ja. Maar ik zou ze zo eentje kiezen. En de andere zijn ik wel heel aan maar ik zou ik ben daar een maand. En ze hebben een programma. Dus misschien zijn dat ook 2 maanden. Ja. Ja, precies. Dat is echt één bezoek in Nederland. Ja, dat zal ik ook. Best. Oh. Hij was toen aan het doen.
Yeah, you can pass.
By the way, I don't get it's very much.
Yeah.
Oh, okay, so no, yes, it's very good. And he graduated earlier than me. Okay. Work there and
Yeah.
Yeah. It's strange.
Yeah.
Yeah. I think we have to get it. Yeah. Yeah, it's yeah, because here it's not buy it and yeah. Yeah. No, it would be something that's somewhere.
Yeah. Yeah,
Tutto a posto, lei? Bad weather. Mic check, mic check, mic check. 5 minutes for the people online. Three more minutes and then we start.
You can say.
Welcome to all of you to the colloquium today of Tommaso and some students in our departments on the topic of in situ making propellants. I'll say it on Mars. Quite a challenging topic. Study of the process system integration, modeling, and critical evaluation. And the coming, let's say, half an hour, max 25 minutes, Tommaso is giving you all the details of this research. And I give the floor to you.
Good morning. Mic is good. Too loud? That's good. Okay. Good morning, everyone. Today, we're going to talk about Mars in situ propellant production, the work that I've been doing for the past 8 months, and in particular, the design and modeling of an in situ propellant production plant for SpaceX Starship rocket on Mars. So the goal is to go to Mars within 10 years. It's a challenge that SpaceX took by first hand, and as well as the Mars Society have done a fantastic job in spreading the word and raising awareness about the topic. SpaceX have developed Starship. Starship is the rocket that is going to take us to Mars, and it's made its maiden flight in the April of this year. Starship has an engine that is called the Raptor engine that uses a deep cryo-metalox combination, which means that it combines methane as fuel and oxygen as the oxidizer to have combustion and then the thrust to leave this planet. Not only will we need a rocket to go to Mars, we will also need technologies to survive on the red planet. NASA have been working for many years, and they actually developed guidelines in order to have companies design these technologies that would allow us to survive on Mars. And some of these technologies use what is called in situ resource utilization, or ISRU. ISRU basically means that you use the resources that are already available on Mars to produce whatever you need to produce. As a part of this work, I visited the European Space Agency. I have to give thanks to Louis for allowing me to do so here in Noordwijk in the Netherlands, in the research center. And I work with some researchers who actually work directly on these topics. And they greatly helped mine as well. So the goal today is to design and model a propellant production plant on Mars. Now, let's talk about the Mars mission. The trip is expected to last 6 months for a mission duration of 3 Earth years. So 6 months to go, 2 Earth years on Mars, and 6 months to come back. But the conditions on Mars are really challenging. So it's really cold on Mars. It's an average temperature of negative 63 degrees. It can get warm during the day, but very cold during the night. I have to say, it doesn't rain on Mars, so it's already better than the Netherlands. We will need power on Mars. NASA has developed the Kilopower project, which is a nuclear reactor that uses the heat of the decay of the enriched uranium in order to produce heat that runs the Stirling engines. And they actually proof-checked this technology. It's ready to go. And they scaled it up to 10 kilowatts. So for now, the largest size that they managed to accomplish is 10 kilowatts of electric power that this reactor can produce. Moving on, the first step of any thesis is to develop the research question, which in this case is the following. What is the most feasible design and modeling of a full-scale rocket propellant production plant on Mars? Now, it's a very broad challenge, so it was decided to divide it into 3 sub-questions. The first one deals with the design of the plant. The second one deals with the modeling of the plant. And the third is a more theoretical aspect that we will see later. And it's more the theory. So by design, what do we mean? We mean how to integrate NASA's guidelines in the design of the plant. By modeling, we mean how do we exploit the Martian environment in order to make our plant as efficient as possible. And the theoretical approach, which we will see later on, is the development of a methodology for an exergy analysis on a different planet. So let's start from the rocket itself. Starship is the rocket that is going to take us to Mars. The goal is to have Starship land on Mars unfueled, completely empty, to produce the propellant on site, and then to have the astronauts return to Earth. Now, one of the goals of this work is to understand the cost efficiency of this. So Starship has two tanks, one for methane, 267 metric tons, one for oxygen, 933 metric tons, for a total mass of propellant to be produced of 1,200 metric tons. In this work, we will design a production system which will have an X metric ton of mass. And one of the goals is to compare how much lighter this is than the propellant we have to bring to Mars. Now, let's talk about how we're going to produce the propellant. So it's methane and oxygen. The chemistry of the plant is really simple. So at the bottom of the screen, you see the outputs, which are oxygen and methane. Let's start from how we're going to produce the oxygen. The oxygen is produced by splitting the water into hydrogen and oxygen via the electrolysis reaction. So 4 moles of water give us 4 moles of hydrogen and 2 moles of oxygen. So as you can see, one of the inputs that we will need is water. Now, the splitting of the water gives us hydrogen, which combined with CO2 via the Sabatier reaction gives us methane. It's a reaction that was discovered many years ago, but remained dormant because methane on this planet is very available under the ground. Now it's facing kind of a renaissance since it's important to produce methane sustainably. And in this way, even on Earth, you can produce methane with green hydrogen and captured CO2. And our energy infrastructure is already working on methane. So this would be a way to produce methane on Earth as well. Let's go back to Mars. So as mentioned, by combining 1 mole of CO2 and 4 moles of hydrogen, we get 1 mole of methane and 2 moles of water. The water can be recycled back, and the methane is our product. So as you can see, we need 2 inputs for our 2 outputs. Now, if the chemistry is clear, we can move on to what the roadmap of today's presentation is going to be. In order to produce our propellant, we need to identify these resources that are available on Mars, if they're available on Mars, how we're going to extract them, how we're going to process them in order to get our outputs, and how the modeling has been carried out. Then we will look into the exergy analysis, which is the biggest contribution to the literature of this work, and how the seasonal variance affects the plant's performance. Lastly, we will look at the KPIs, which are the key performance indicators, which help us quantify the results. Let's get started from the resource identification. So our 2 inputs are CO2 and water. The CO2 is very present on Mars. The Martian atmosphere is made up of 96% of CO2 by volume, which means that the by mass is even more. The remaining 4%, this is the interesting part, it's argon and nitrogen. Argon and nitrogen are inert gases. This means that they don't react in any reaction. So it's important to notice how we can grab the Martian atmosphere and have basically very pure CO2, and the remaining gases don't really interfere with our reactions. So it's important to degas them at the end of the day, but they don't pose a threat to the plant. The next input is water, and contrary to popular belief, there's a lot of water on Mars. So millions of years ago, Mars used to have oceans and rivers just like Earth. Then a catastrophic event happened, and now there's no water on the surface, but it's all under the ground. So water can be found in 2 ways: under the ground, in the form of ice, and in the rocks itself in the form of hydrous clays and hydrous silica. So water is there, CO2 is there. How do we get them? The CO2, as mentioned, is already very pure, and the gases that are present don't pose a threat, so we can simply take it, compress it to the operating pressure of the reactors using a scroll pump compressor. The Martian atmosphere is very thin, with atmospheric pressure on average of 600 pascals, so it's going to be a big delta P to compress, nothing that a scroll pump compressor can't do. The operating pressure of the reactor is 3 bars or 300 kilopascal. So this is how we're going to compress the CO2. The water is a different story. So the water is in the form of ice and it's buried under the ground. So this is a technology that was developed by Honeybee Robotics, who I had the pleasure to talk to and see their presentation last week in Tempe, Arizona at the Mars Society Convention. And I talked to the developers of this technology in order to know more, since I use their technology in my work. Basically, it's a drill that will go under the ground for hundreds of meters, break through the ice, find the purest ice that there is, which is very deep. Again, hundreds of meters, they were talking about kilometers as well. They are gonna chop the ice into cubes at the bottom of this tube, of this drill. And then they're gonna use microwaves to melt it and bring the liquid water up. It's a sound technology that was already awarded a contract by NASA. So yeah, I use this for this work. Let's move to the process. Now, what you see in the figure is the block flow diagram of this plant. So as you can see, here are our inlets, CO2 and water. So the first step is to compress the CO2, which you can see is done by 4 stages of scope pump compressors for a total of 14 kilowatts. The water, on the other hand, is split by a solid oxide electrolyzer. So it's split into hydrogen and oxygen, of course. Now, this is the heavy duty part of the plant, power-wise. The technology of SOEL, or solid oxide electrolysis, was chosen for 2 reasons. The first one is the efficiency. We will need a very efficient machine on Mars. Money is not a problem. So SOEL is expected to have a very high efficiency heading into the future. The second one is the compactness of the machine. It's a very compact machine that splits the water in the gas phase rather than in the liquid phase. And it's invertible. So by simply switching the switch, you can use it as a fuel cell. Now, moving on, you can see at the top of the screen, the reactors. So the result of the simulations were 3 in-series reactors where the methane is produced. Now, we also produce water, if you remember the chemistry. So after every reactor, there is a condenser that takes the water away and recycles it. It's important not to have water going into the next condenser to improve the efficiency. Then the products are liquefied. Now, we need to liquefy the products because storing them in gas phase would be very dangerous and not efficient at all. So by liquefying the products in this cold box, we make sure that they're very, for density reason, they're very dense. So the cool thing is that methane and oxygen have very similar boiling points with a difference of only 4 degrees centigrade, which means that you can liquefy them using the same nitrogen loop. So one machine liquefies both streams, and the chosen technology again is a liquid nitrogen loop with a nitrogen compressor for a power requirements of 173 kilowatts, which, if we sum all these up, we get a total power required for the plant of 644 kilowatts. Now, I talked a lot about the simulations, but what are the simulations? So the simulations were carried out on 3 different softwares with this goal: maximize efficiency, minimize equipment mass. The lighter the plant is, the easier it is to bring to Mars and the cheaper it is. So the first software that I used is Aspen Plus. Aspen Plus is a process engineering software for process plant design, where the sensitivity analysis were carried out. Sensitivity analysis just means finding the optimal point for temperature, pressure, and so on. Heat integration, so how the heat is exchanged within the plant, and any type of simulations that require thermodynamic values. The second software is Python. It's a programming software where the scripts for the equipment sizing were written, the dynamic simulations were carried out, and the exergy analysis, which we will see later on. And then Excel for general data analysis and equipment sizing. Now, the biggest contribution of this work to the literature, the exergy analysis. So as you can see, this is the definition of exergy, the maximum obtainable work that can be extracted from a system when it interacts with its surroundings. You have to think about exergy as a way to quantify the quality of the energy. So in our input-output structure, as you've seen before, in our block flow diagram, we had 3 types of streams. Material streams, so CO2, water, methane, oxygen, and everything that happens in the middle. Heat flows and work flows. So let's talk about material flows. Material flows have an exergy that is given by two contributions. The first one is physical exergy, the second one is chemical exergy. Physical exergy can be computed, of course, the addition gives us the total exergy of the stream. The physical exergy is computed directly on Aspen Plus. You simply have to give the new reference state, which on Mars is 210 kelvins and 600 pascals. And Aspen simply computes the values of the physical exergy. But material flows have another component, chemical exergy. And chemical exergy values are found on tables under Earth standard conditions. We need to find a way to compute these chemical exergy values under Mars's standard condition. So this is the hard part of this presentation. Stay with me. The way that this was developed was to understand, first of all, what the reference state is. The reference state is the Martian air. The Martian air, we've seen before, is made up of 96% CO2, 2% nitrogen, 2% argon, and then there's traces of water and oxygen, which is really important. This is because by understanding this standard fluid, which has a standard temperature of 210 Kelvin and a standard pressure of 600 pascals, we can compute what the chemical exergies of the molecules present in the atmosphere is using this, using this formula right here, which comes from the definition of exergy and the ideal gas law, and we combine them together. Well, yeah. So by calculating what the partial pressure of every of these components is in the Martian atmosphere, we can calculate what the chemical exergy under the new standard conditions is. What about the molecules that are not in the Martian air? We do it by using the methodology developed by Dinsler et al., which I cited in the previous slide, whereby simply computing the new standard free Gibbs energy of formation of the chemical reaction that we saw before, and using this formula right here. So the chemical exergy of methane is equal to the new, under new standard conditions, 210 Kelvin, Gibbs free energy minus 2 times the stoichiometric factor of water, because it's on the same side as methane, plus the exergy of hydrogen and the exergy of CO2 with the stoichiometric factors. And we get the chemical exergy of methane under these new standard conditions. Same thing we do for the hydrogen. Ta-da. So this is how this was carried out. Now, by computing the so by adding the chemical exergy and the physical exergy, we get the exergy of the material streams. Now, if you remember, we have two more streams to look into: the heat flows and the work flows. Now, work is considered pure exergy. This is because electricity is the purest form of energy. So 1 kilowatt of electricity of work is equal to 1 kilowatt of exergy. Heat flows, though, need to be multiplied by the Carnot factor to get the exergy. The Carnot factor is a factor that takes into account the quality of the heat. This means that by using this formula right here, and by dividing the ambient temperature by the temperature at which the heat is exchanged, we get the exergy of the heat flow. So a heat flow exchange at a higher temperature is going to have a higher exergy because it's of a higher quality. So by doing so, we've computed all the streams we needed: work, heat, and material. Now we can compute what is the second law efficiency of the plant, which is the ratio between the input exergy and the output exergy. And it amounts to 62.7% in this case. In a second. Now let's move on to the dynamic behavior of the plant. In 2011, NASA sent the Curiosity rover to Mars. And since then, it has been gathering data about temperature, pressure, solar irradiance, and so on. By gathering this data and picking an interval of 1,895 sols, 1 sol is 1 Martian day, we can compute the pressure profiles and the temperature profiles on Mars at the site where the rover was. So as you can see, it's basically 3 Martian years, summer, winter, summer, winter, summer, winter, and so on for the pressure. Now, by doing so, and by combining the data of our plant with this data, we can see how the plant interacts with the environment and how the changing environment makes the plant behave differently. You have to imagine that the plant interacts with the environment in two ways. The first one is directly by taking fluid from the environment, in the case of the CO2 coming from the atmosphere. So as you can see, in the summer, the CO2 is going to have a higher pressure, and in the winter, a lower pressure. This means that if the compressors have to compress the CO2 to a certain amount of pressure, and in the summer, it's already a high pressure, the compressors have to do less work than a lower pressure in input in the winter. So the utility, the load of the compressor changes with the changing pressure and, of course, temperature of the CO2. Now, another way in which the plant interacts with the environment is by dumping heat from in the environment and by taking heat from the environment, so exchanging heat. As you can imagine, the temperature is a key factor. So in the summer, hot day, the coolers that need to cool, dumping heat to the environment are going to work less efficiently. And in the winter, during the night, when it's very cold, the heaters that are using the heat from the environment are going to work less efficiently, and so on. So by combining all this data, the plant operational data, the weather data from Mars, we can see how the behavior of the plant changes, and we can size the equipment in order to be able to withstand any environmental condition. So the coolers can be able to withstand the harshest nights, and the heaters the harshest summer days. The results are available on the paper, on the report. Now let's look at the KPIs. KPIs are key performance indicators. So we've talked about how the work was carried out, but it's important to quantify the results. KPIs allow us to quantify the findings, and they also allow for cross-referencing among peers. This means that if somebody else wants to pick up my work and redo the experiments and hopefully improve them, they can exactly see how the results were computed and compare them. In this case, 3 KPIs were chosen, one for every sub-question, in order to quantify exactly the research question and the sub-questions. So the first KPI is the ratio between the equipment mass and the propellant mass that needs to be produced, which is 11%. This means that by producing propellant on site, we save 89% in launched mass from Earth. The second KPI, we talked about the modeling and how to increase efficiency. So the second KPI is the specific energy consumption, which is the ratio between the power and the product flow, which amounts to 6.52 kilowatt hours per kilogram. And the third one, a more theoretical aspect, we've seen it before, is the second law efficiency, which is equal to 62.7%. Now, moving on to the conclusions. In situ propellant production is key to human missions to Mars. We need to find a way to get the astronauts back. And by doing so, we save 89% in launched mass. And money is a big factor in the space industry. This work gave them a methodology on how to conduct an exergy analysis on a different planet and how to calculate the chemical exergy of species on Mars. The first recommendation is to investigate increasing the efficiency of the equipment. If we make the electrolyzers more efficient, the whole plant is going to be more efficient. If we make the compressors more efficient, the whole plant is going to be more efficient. And the second recommendation is to investigate how to respond to intermittency of energy sources. I've shown it before at the beginning of this work. Nuclear power was taken as the power source, but solar power is also available on Mars during the day. So it would be interesting to show how the plant will ramp up during the day when solar power is available and ramp down during the night when it's not. Before I finish, I want to leave you with something. In 1969, we sent a man to the moon, and it opened a window which people hoped would have us today in 2023 among the stars, but we're not. It triggered a technological revolution. But something happened, and the last man that stepped on the moon was only 3 years later, in 1972, when the astronauts of the Apollo 17 mission were the last men to ever step on the moon. The purpose of this work was not only to investigate the engineering behind the Mars missions, but to raise awareness about this topic. The window is about to open for us to go to Mars. SpaceX have developed the rocket, it's ready, we need to go. So it's important to understand how the trip to Mars has the opportunity to spark another technological revolution, as the technologies that we will need to develop to survive on Mars are also going to aid life on Earth. So most of all, the trip to Mars is about hope for the future, and pushing boundaries, because it will show the world how even the most impossible challenges can be overcome and how limits, like fears, are often just an illusion. Thank you.
Thank you. I open the floor for questions because I think it will trigger.
You want the mic?
Sure.
If it works.
Does it?
I don't think-
No, okay.
You can scream, I'll repeat it for the.
Yeah.
First of all, thank you for the presentation.
Thanks.
It was very fun. I was wondering, as the solid oxide electrolysis to your production scheme efficiency, correct me if I'm wrong, you sure that also operates quite an elevated temperature. I saw on your asking plus that there was heat integration. I was wondering if you elaborate on some of the steps you took there, and also the question I had was you mentioned at the end your intermittency issue with power sources. Could, for example, high level of temperature pulling your solid oxide be used, say, in battery scheme to cancel some of that out?
Okay, for the people online, the question is why solid oxide electrolysis? Because it operates at a high temperature. This back way. So thank you for your question and the compliments about the presentation. So we have a lot of heat available in our planet. So if I go back for a second, give me a moment. All the way back. There we go. So these three reactors operate at three different temperatures in the between 300 and 400 degrees centigrade. But you need to liquefy the water here. So from here to here, you're basically losing all the heat because you need to go down to 90 degrees to liquefy the water. So this heat is actually used to heat the water in the input. So you have three heat sources where the heat would be lost otherwise. So you already have some heat that you can recover from there. And then the cool thing was that the water is actually heated by burning the hydrogen and the oxygen that you produce in the electrolyzer itself. So by designing a burner that is 21 kilowatts in heat load, so not much, by oversizing this electrolyzer, where you produce more oxygen and hydrogen than you just still come out and you burn them to heat the water. So basically it's a closed loop. This again is just for the heat that you need that you don't get from up here. The heat integration is very complicated. It's a very bulky system. I mean, one of the recommendations would be also to increase the efficiency of the heat integration. But yeah, I don't know if it answers your question. And about the solar power, I haven't looked into it honestly, because we talked a lot with Vibran about these energy sources, how to integrate them. Can we use solar? Can we use some dynamic simulations? But for the purpose of this work, we did it. But yeah, I mean, maybe if you want this thesis, you can work on this. Is that it? Yeah, good. Okay, thanks.
Maybe a little bit of follow-up question. We use this nuclear and NASA developed nuclear units that are each 40 kilowatt. Do they also produce sort of waste heat that you somehow use and use?
That's a good point. I don't think so, because it's a Stirling engine that uses calcium as a working fluid. So I think it's a very close system. I mean, I'm sure they made it very efficient.
Okay.
But I think the answer is no, but I'll look into it better if you want. Thank you. Maybe online. Oh, give me a second.
In the meantime, you talk about the water sourcing, company and so on. Do you consider it important to, or would the energy involved in pre-treating this water be significant or not? Is it water or other minerals?
Yeah, so it's I'm gonna answer to you the way they answered to me last week in the US. It's very pure water because you're going down hundreds of meters in the ice. So it's water pure to the third digit in the percentage. So it's 99.9% pure water because it's been there for so long that any mineral is kind of like dropped out. So they can find these pockets of pure water on Mars. Yeah, I mean, there's gonna be some purification system. We need a purification system, but they didn't talk about it. So, to my knowledge, there is not work being done yet. But they went to the Arctic, they drilled, they drank the water from millions of years ago. It was that.
Yes.
Which also the cost of this plan?
Yeah, as they say. So cost in mass, yes. So the mass of the plant is 11% of 1,200 metric tons. Dollars, it's really hard because right now, no amount of dollars can take you to Mars because no one has ever gone. So it's hard to quantify in dollars. I listened to a podcast where Elon was talking about how right now the price would be $10,000 per kilogram or 10 millions per ton. But again, it's a figure taken out of, his brain. So it's hard to quantify in dollars as long as we don't go. Go ahead.
Okay, my question was, thank you for the presentation. How is that such a large amount of power generated on this?
Yeah, so good question. So the biggest nuclear reactor that they built is 10 kilowatts. So right now you would need 65 nuclear reactors. It's important to scale the technology. I'm sure that they will. So in the last 10 years, they went from 1 kilowatt of electric power to 10. So they already scaled it up a bit. But it's better when you do this type of missions to have a lot of small things, because if you build a very big reactor, say 700 kilowatts, and then it doesn't work, you're screwed on Mars. So you need to be able to have small units that are perhaps a bit, able to, you can listen to this type of issues. Thank you. There was another one? Yeah, go ahead.
I actually have a different question, but following from that, your nuclear firm takes the weight of the plant compared to the weight of the fuel. The plant would not work without power generation, and not include the weight now.
It's included. Yeah.
Then I have an actual question because, so the question, you have a skilled plant. You mentioned a six-month journey, 2 months, 2 years there, 6 months back. How does your production rate compare to the 2-year stay? Is the fuel done the day of departure? Is there a window you can stay?
Good question. Good question. Thank you. No, of course, the best way is to produce it throughout the mission, because in that way you divide the mass of the fuel, which is the propellant, which is 1,200 metric tons, by the largest amount of time that you can, which is 500 sols, which is 500 Martian days. So the mass flows are very small. So the trick is to produce it consistently, bit by bit, throughout your whole mission stay. Of course, there's gotta be some safety factors taken into account. You need to be ready a bit before, I'm sure. You need to actually, and this was taken into account, the rocket doesn't use liquid propellant, it needs densified liquid propellant. So you need to densify the liquid, so subcool it. And that was not part of this work because the subcooling happens a few days before the rocket takes off. So that's some days you need for the subcooling. Some days you want, you're gonna get there and you have to set it up with robots, I don't know. So, but yeah, the time frame that was taken into account was 500 sols out of a 600 sol mission. So 5, 6, and you produce the propellant consistently with no changes.
If not, then I close this session, and of course for the committee there will be ample time to ask questions at Process and Energy Department. Thanking you once again for this presentation.
I would like to. I want to thank Professor De Jong because without him, this thesis would have never happened. I went to him with an idea and he believed in it. And I think we've come a pretty long way. So thank you very much for really allowing me to do so.
Procedure now is as follows that, yeah, we have a 1 hour session, question answering, going through the theory, the report, etc., modeling. And after that, a bit more than an hour, I think, yes, evaluation, and then, yeah, we'll have the final outcome.
Okay. Which is in the process.
Which is in the process
Yeah, okay.
department, the colloquium room there.
Yeah.
That's the first hour. It's
Yeah, private, yep. Okay, thank you.
Yeah. And the committee, I want to say, first of all,
Thank you.
Ora mi devo vorrei passare per un'ora. Vai, guarda, lo sai che sei il numero uno.
Grazie, aspetta, scusa che devo...
Benissimo.